Welcome back to this next video in which we are discussing field extensions. Okay, right, so in this next video what we're going to do is study in a little bit more detail how addition and multiplication actually work in our field extension, just to make everything absolutely concrete about this field extension. Okay, now just before I do that, what I'd like to make a comment on is this polynomial p of x that we generated the principal ideal of in order to quotient out the ring of polynomials over the field, capital F, using. Okay, when we initially stated the properties that we wanted this polynomial to obey, we said that we wanted it to be irreducible and we wanted it really to have degree greater than or equal to 2, so that we could conclude that it has absolutely no roots in the field capital F. And what I'm going to add now is the fact that you can always assume that it is monic, okay? Because if it's not monic, you can always modify it to become monic just by multiplying by a constant polynomial, which is of course a unit. So you can modify it by multiplying by a unit, and therefore you can turn it just into another associate of itself. Okay, and that will generate the exact same principal ideal as the original polynomial p of x, so you'll get the exact same field extension. So let me make this a little bit more concrete by writing something down. Okay, so let's say we originally had this polynomial p of x, which we suppose was irreducible and of degree greater than or equal to 2. So p0 plus p1 x plus, and we never originally assumed that it was monic. So we might have had some coefficient pn x to the n here. Okay, we have now successfully constructed this field extension by taking the ring of polynomials over the field and quotienting out by the principal ideal generated by this polynomial. What I'm going to show you now, okay, and what is going to become useful in just a moment, is that we might as well assume that it's monic, okay, because what we can do is we can just multiply this by the multiplicative inverse of Pn, which of course is just a constant polynomial in the ring of polynomials over our field, and what we will end up with is the polynomial P0 over Pn plus P1 over Pn times x, plus all the way up to, and then the leading coefficient, the coefficient in front of x to the n, will now just be 1, okay? And you could quotient your ring of polynomials out by the principal ideal generated by this polynomial, and you would end up with the exact same field extension. Okay, so of course what we did is we took the ring of polynomials over the field capital F and we quotiented out by the principal ideal generated by the polynomial p of x. I am now saying that you could substitute in here, instead of using this polynomial, use this monic polynomial here. Okay, it would generate the exact same principal ideal. I hope that's obvious, okay, because this will be in the principal ideal generated by this polynomial, because just multiply this polynomial by Pn and you'll get this one, okay, but this one will also be in the principal ideal generated by this one, because multiply this one by 1 over Pn and you get this, okay, and whenever that's true, the two principal ideals will just be equal to one another. So the principal ideal generated by this and this are exactly the same, and therefore you're quotienting out the ring of polynomials by the exact same principal ideal, so you get the exact same field overall. Okay, and of course, if this one was irreducible, then any associate of it is still going to be irreducible. Multiplying by unit doesn't change irreducibility. Okay, so this polynomial is still going to be irreducible in the ring of polynomials over the field capital F. So from now on then we will assume that the polynomial that we quotiented out by was a monic polynomial. You might as well use the monic polynomial. Okay, it will help us with interpretation later on. Okay, right. Only slightly, I mean, it's not going to hugely change anything, but people often do make the assumption that you understand that we can just use a monic polynomial. We might as well, because they're very nice. Okay, so it's an important line to have in this video at some point. Okay, so now let's go on to what I said we were going to do in this video, which is exploring addition and multiplication in our field extension. Okay, so we've now seen that our field extension K, all of the elements consist of things of this form: a0 plus a1 theta plus all the way up to an minus 1 theta to the n minus 1. And remember the additions and multiplications here, those are all just additions and multiplications in the field capital K here. Okay, and indeed we know that 1 theta all the way up to theta to the power of n minus 1 forms a nice basis for our field extension K viewed as a vector space over the subfield F. Okay, so now let's explore how we actually add two elements together. Okay, so if I took two elements of my field extension K, okay, so let's say I've got one element here, A0 plus A1 times theta plus all the way up to an minus 1, theta to the n minus 1, and I want to now add this to another element which is of the form B0 plus B1 theta plus all the way up to Bn minus 1 theta to the n minus 1, okay, where the a's and the b's here are all from the subfield capital F, our original field. Okay, well this is almost trivial because all of the additions and multiplications here are in the field capital K. This is an addition in the field capital K, so of course how can we do this? Well, it's very, very simple now. All we're going to do is rearrange it because we know it's a field, so addition is going to obey associativity and commutativity, which is why I haven't bothered putting any brackets in, and now why we can move everything around. So we'll bring the two terms that are in front of one effectively next to each other. Okay, so we'll have A0 plus B0 here, and we might as well put brackets around that nicely. Then we'll bring these two terms that are in front of, well, which have a theta in them next to each other, and then we'll factorize out the theta because again we're working in a field, and multiplication in the field is going to distribute over addition, so we'll get, oops, not like that, A1 plus B1 times theta there. Okay, and then it will go on, and you'll do this for each of the powers of theta. So for this final one, theta to the power of n minus 1, you'll bring the two terms next to each other, and then you'll put out the theta to the power of n minus 1, and you'll get plus an minus 1 plus bn minus 1 theta to the n minus 1, and everything here is just addition and multiplication now in your larger field extension K. Okay, so effectively if you want to understand how two elements add and multiply, sorry, not multiply yet, just add in your field extension, all you're going to do is just add the coefficients in front of these powers of theta. Okay, we know we can express any element in this field extension of this form, okay, where it is just a linear combination of this nice basis of these nice basis vectors in this nice basis. Okay, well you can just add the coefficients effectively, and those, because those are both in the subfield capital F, and because the addition in the subfield is compatible with the addition in the larger field, obviously, okay, from what we've proven so far, you can view this as just addition in the subfield capital F. Okay, so you'll now get some new linear combination then of these basis vectors. Okay, so addition is extremely easy to understand as soon as we've got this nice basis to work with. Multiplication, we're going to have to go a little bit further. We're going to have to explore multiplication in a bit more detail. Okay, so addition's very, very simple, and in fact I should probably just put a title here. So this is us exploring addition in our field extension capital K, so I'll just underline that in some nice colour. And now we're going to go on to the more complicated one, but still not too complicated, which is multiplication here. And again, we're going to use the fact that we now have this description of all of the elements as linear combinations of these basis vectors here. Okay, that's going to be very helpful to us. Now initially I want to go to the very definition of multiplication on the quotient ring, and then we'll have another way of looking at it where you use the fact that we now understand the field extension in terms of these basis vectors, in terms of these linear combinations of the basis vectors. But initially let's go back to actually viewing the field extension as this set of cosets. Okay, so how do you multiply two elements together then? Two cosets together. You take representatives from those two cosets, multiply them together in the initial ring of polynomials over the field, get some new polynomial, and take the coset that contains that. Okay, so for instance, if we have two elements then of our field extension and we want to multiply them together, so let's write them out. A0 plus A1 theta, and from now on we will be writing out our elements in this form, okay, plus all the way up to an minus 1 theta to to the power of n minus 1 as these linear combinations of these beautiful basis vectors here, and we now want to multiply them together in the field extension capital K. So we're going to multiply this with b0 plus b1 theta plus all the way up to, let's say, bn minus 1 theta to the n minus 1 here. So we now want to perform this multiplication. So I will show you another way which just now works in the field capital K, but initially let's think about this right back to the foundations of how we constructed this field extension. Okay, this is going to be this linear combination of these basis vectors is just some coset, and we know that that's going to be the coset that contains the polynomial a0 plus a1x plus all the way up to an minus 1x to the n minus 1. So the answer to this, and this of course is a linear combination that makes sense in the field extension capital K, so the additions and multiplications here are in the field extension capital K, but the answer to this, the actual element of capital K that this is just the coset that contains this polynomial. Okay, and we're going to initially remember that in order to multiply these two together. Okay, so this thing here is just the coset that contains that polynomial here. Okay, and remember the meaning has changed now. These additions and multiplications are now in the ring of polynomials over the field rather than in our field extension. Okay, and we are now multiplying this coset in the field extension capital K, or the quotient ring if you'd rather view it like that way, with this element here, okay, which of course will just be the coset that contains the polynomial b0 plus b1x plus all the way up to bn minus 1x to the n minus 1, like so. So I'll put a big bar over the top there. Okay, so here is the answer to that. So remember again, this is addition and multiplication in the field extension. This is a beautiful linear combination in the new field extension. Now this is the actual blunt answer to what this actually would give you if you actually worked it out in the field extension. Okay, the coset that contains this polynomial here. So how do we then multiply these two together? Well, we go to the definition of multiplication in the quotient ring, which is of course our field extension. You take a representative from here, you take a representative from here, multiply them together in the ring of polynomials over the field, and then take the coset that contains the answer. So of course we'll take the representative that we've named this coset after. We'll take this representative and we'll take the same representative here. We'll take the one that we've named the coset after. So we'll take these two polynomials, multiply them together in the initial ring of polynomials over the field, and of course that's defined. You'll get some polynomial which will potentially have degree greater than n, greater than or equal to n. Okay, so the answer to, let me just highlight it, this polynomial in pink here multiplied with this polynomial also highlighted in pink in the ring of polynomials over the field capital F could be a polynomial of much of degree greater than or equal to n. Then of course what you just have to do is find the coset that that's in, and of course you just have to find which polynomial of degree less than n is in that coset, and we know that there will be one and only one polynomial of degree less than n that's in the same coset as that polynomial that you get as the answer. So that's how multiplication works in this field extension, viewed from the core, basically from the bottom up, so from the actual construction that we use to create this field extension. Okay, but we don't actually even need to go that foundational anymore. We can now just think about the field extension in its own right and forget the way that it's constructed now. We know enough to now work this out without going to the foundations of how it's constructed. Okay, so let me give you interpretation number 2, the second way of thinking about multiplication in this field capital K. Okay, and this is why, well, this is where it's going to be helpful to remember that the polynomial that we quotiented out by, we can always think of it as being monic. Okay, so remember, in the field extension capital K there is going to be a root to the polynomial p of x, and that is in fact going to be the coset that contains the polynomial just x, and that of course we've called theta. Okay, so when you take the polynomial p of x and evaluate it at theta, so you apply the evaluation homomorphism pertaining to theta to the polynomial p of x, which is now viewed as a polynomial in the field of, in the ring of polynomials, pardon me, over the field capital capital K now, the field extension, and apply the evaluation homomorphism for this element theta in the field capital K, you're actually going to get 0. Okay, so we know that. Now, why is this helpful then? Well, this tells us that theta obeys a certain polynomial, this monic polynomial. So it's going to be true that P0 plus P1 times theta plus all the way up to, not Pn, I'll correct my mistake by turning that into Pn minus 1, because of course we've assumed now that our polynomial is monic. Okay, so we'll then get plus theta n here. Okay, right, is equal to 0 in our field capital K, is equal to the additive identity in capital K. And note, these additions and multiplications now, they mean addition and multiplication in our field extension capital K. So this is all in the field extension in capital K. Raising to the power, theta to the power of n, that's in our field extension capital K. So this is all pertaining to the field extension capital K. So I'll just highlight that in green there to remind us. And of course this is the additive identity in our field extension capital K. Okay, now, why is that helpful? Well, if we want to multiply these two elements together, okay, we know that the field capital K is a field, okay, fundamentally it's a field. All of these additions and multiplications that I've got here that make up these elements, okay, I'm describing each of the elements as a linear combination with the additions and multiplications in the field capital K of these basis vectors in this way. The advantage of doing that is that if I want to multiply these two together, I can just now apply distributivity. Everything, every operation here is just in the field K. We know that the field K has to obey distributivity, so I can just multiply this huge great thing out. I can take A0 and multiply it with every single one of these. Okay, I can take this one here and multiply it with every single one of those, and then just turn it into a massive great big sum. Okay, so if I write this more concisely, then it will be the sum from I is equal to 1 to, we'll need 0 actually. Sum from I is equal to 0 to n minus 1. The sum from j is equal to 0 to n minus 1. Okay, and then what you'll get is the ai times the bj, and then you'll add the powers of theta, because of course when you have theta to a power, it now just means multiply theta that many times. When you multiply that with some other power of theta, which is multiply theta that many times, of course it is just multiply theta with itself I plus j times. Okay, so that is the way that the powers of theta, where we're viewing the power as actually being taken in the field capital K, is going to work. It's the way it has to work. Okay, so there is absolutely no definition there. This has to be the way that it works because K is a field. Okay, so the instant we decompose our elements of the field extension capital K into these linear combinations of these basis vectors, multiplication is just going to be this great big sum where all of the sums are in the field extension capital K, and in principle you could work out what the element there actually is. Now, of course, it's very nice to have all of the elements described as just linear combinations of these basis vectors. This might not end up being a linear combination of those basis vectors. We would like to reduce it back to being, and the reason it might end up not in the form of a linear combination of these basis vectors is because you might end up with higher powers of theta. So we need to have a way of understanding what happens when you take higher powers of theta, okay, when you go higher, because of course you can ask, okay, theta is just an element of the field capital K, you can take higher powers of theta, okay, but what we need to know is how can we write these higher powers of theta as linear combinations of our basis vectors, which are the lower powers of theta, which we know all elements of the field extension can be written in. So you can ask about higher powers of theta, but why on earth would you? Well, obviously here we are going to need to ask about them, but normally we describe all of the elements with these linear combinations of these lower powers of theta. So we need basically to find the higher powers of theta as linear combinations of the lower powers of theta. Okay, we can work this out, but what we want to do is work out what is the linear combination of the lower powers of theta that this is equal to, and for that we need to understand these higher powers of theta, and this can give us insight into the higher powers of theta, because now what I can just do is rearrange this. I can turn this into theta to the power of n is equal to the additive inverse of Pn minus 1 times theta to the n minus 1 plus the additive inverse of, don't know why I'm doing Pn minus 2, but we'll do it now since I've written it, times theta to the n minus 2 plus, and then it will go all the way down to plus the additive inverse of P1 times theta plus the additive inverse of P0 in that way. Okay, so here up we go. Of course, we know in a field that when we have, or indeed in an arbitrary ring, when we have the additive inverse of a product of things like this, you can just make that will just be equal to the additive inverse of one of the things in the product times the rest. So here we've got the additive inverse of Pn minus 1 times theta n minus 1 times. Basically, that's going to just equal the additive inverse of one of those things times all the rest left the same. Now, of course, you could pick one of the thetas to be the additive inverse, but why would you again? Okay, we're trying, remember, to find higher powers of theta as linear combinations of these lower powers of theta, so of course we'll make the coefficient the additive inverse bit. So we'll take the additive inverse of Pn minus 1, the additive inverse of Pn minus 2, the additive inverse of P1, the additive inverse of P0, okay, and then of course we'll have theta to the power of n written as a nice linear combination where the coefficients are in my subfield, capital F, of the lower powers of theta. So this is all looking very nice. So I can now deal with theta to the power of n. I can now write theta to the power of n as a linear combination of these lower powers of theta. Okay, so that's excellent. Now what I need to do is even higher powers of theta. Now how does this work? Well, what I can do is I can consider, okay, theta to the power of n plus 1, that's just theta to the power of n times theta. So just multiply all of this with a theta, apply distributivity here, it will become the additive inverse of Pn minus 1, theta now to the power of n, plus the additive inverse of Pn minus 2, theta to the power of n minus 1, plus all the way down to the additive inverse of P1 times theta squared now, plus the additive inverse of P0 times a theta. Okay, so I've just multiplied both sides here with theta, so this is a perfectly true statement. Okay, and now it's a little bit disappointing because what was I trying to do? Remember, I wanted theta to the power of n plus 1 written as a linear combination where the coefficients are from my subfield, capital F, of the lower powers of theta, and I have got theta to the power of n here. I want just theta to the power of n minus 1 downwards. I don't want theta to the power of n there, but that's okay because now I can just substitute this expression in for theta to the power of n, and then I'll return this to just being a linear combination of the lower powers of theta, the powers of theta lower than n. Okay, and you can go on like this. Once you've got theta to the power of n plus 1 written as a linear combination of the lower powers of theta, you can then do theta to the power of n plus 2. Again, that's just theta times theta to the n plus 1. Okay, so just multiply this side by a theta, and you'll again get one of these powers of theta being turned into a theta to the power of n, and again you just substitute this in again. So you can just work your way up in this way, and you can write all of the higher powers of theta as linear combinations of these basis vectors of these lower powers of theta where the coefficients are from our subfield, capital F. So we knew that must be the case because we know all the elements in our field extension are linear combinations of these basis vectors. Okay, we just needed to be able to find a way to actually do it. So now when we do actually multiply these two together and get a great big expression like this, we now know how to handle these higher powers of theta. We can stick these in basically, okay, which we get from our monic polynomial which we used to initially generate the field extension. Okay, right, so we can stick those in and return this down to just being a linear combination of the basis vectors, those lower powers of theta. That's another way of thinking about multiplication in this field. Again, that has the advantage that you don't have to go back to the foundations. Okay, this is all done in the field now that we understand enough about this field extension. Okay, right, so we will call it there for this video. We'll have a break now, and in the next video what we will do is we'll start off with a bit more notation concerning field extensions, and then we'll introduce an extremely important theorem concerning field extensions.